Hello, I'm Brian Young, and today we're doing Module 26201, Alternating Current. Let's get started. Alternating Current 26201. Successful completion of this module prepares you to do the following: identify AC waveforms, determine unknown values in an AC circuit, make power calculations in AC circuits, identify transformers and explain how they operate. This is a knowledge-based module. There are no performance tasks. For safe and successful electrical installations, it's important to have a sound understanding of both direct current and alternating current electrical principles. AC electricity also has a frequency component, so knowledge of AC waveforms and the effects of reactive and inductive components in a circuit is essential. This module describes AC circuits and explains how to apply Ohm's law to resolve unknown circuit values. 1.0.0 AC waveforms. Identify AC waveforms. Define the terminology of sine waves. Define AC phase relationships and identify non-sinusoidal waveforms. Alternating current is a type of electrical current where the direction and strength or voltage of the current changes over time. This change happens in a pattern called a waveform, where the current goes back and forth between positive and negative polarities. Here's a highlight. It says two principles form the basis of all electromagnetic occurrences. This one's highlighted. It says an electric current in a conductor creates a magnetic field that surrounds the conductor. Movement between a conductor and a magnetic field creates a voltage in the conductor only if one of the components is moving perpendicular to the direction of the field. Okay, so let me go to my 3D BB. I'm going to draw some things. In order that I not get in the way, I think I'm going to go hide. Okay, in order to understand alternating current, we need to do a little review of current, voltage, and resistance. So here's a wire, and when I put a current through this wire, it creates a magnetic field that encircles this wire. And there's a certain rule. It's the left-hand rule. I didn't draw a picture, but when I wrap my fingers around the wire such that my thumb is pointing in the direction, well, that's a horrible drawing. I should have done it earlier. But when I wrap my fingers around this wire in such a manner that my thumb of my left hand is pointing in the direction of current flow, then my fingers will wrap around this wire in the direction of the magnetic field. So here's my left thumb, it's pointing in the direction of current flow, and my fingers are wrapping around the conductor in this polarity or this direction. So I can represent that over here by showing this is the conductor, and here's the current. When I draw the current, I'm going to draw an arrow. I'm either going to draw the tail feathers of the arrow, or I'm going to draw the point of the arrow. So you'll see the tail feathers going into the chalkboard, or you'll see the point coming out of the chalkboard, or the 3D BB. So when current is coming out of the whiteboard, if I use my left hand, we'll see that the orientation of these magnetic lines of flux are clockwise around this wire. And when the current is flowing into the whiteboard, using my left hand, we'll see the orientation of these lines of magnetic flux are wrapping around counterclockwise. All right, so that's the left hand rule. There are a couple of different left-hand rules. I forget whose left-hand rule this is. I want to say Lenz's law. That's the difference. Okay. So if we then take this wire and we form it into, I'm just going to get a new page here. If we take that wire and we bend it into a coil, that magnetic field will, it'll intensify. It's an additive. It's additive. So that these lines of magnetic flux are going to actually multiply. They're going to become stronger. And I can make it stronger still by taking an iron core and inserting it in this coil. There we go. I can put this iron core inside of the coil, and it's going to intensify or strengthen those lines of magnetic flux even more. It concentrates them, all going in the same direction. So it becomes a much stronger magnetic field. And you can do this at home. You can do this with a 9-volt battery and paper clips and a nail. You can take a piece of wire, wrap it around a nail, and connect both ends of the wire to the 9-volt battery. And you'll see that you're able to pick up paper clips with the nail. It's kind of fun to do, especially if you have kids in the house. They can help you with it. But it'll intensify the magnetic lines of flux. It concentrates them by giving them a place to go. So when we put a current through a wire, we create a magnetic field, and we can intensify that magnetic field by wrapping these into a coil. Well, the opposite is true also. The opposite is true, so that when I take a wire and I move it through a magnetic field, if I have two magnets, and here's, well, I could use north on this one, north and south. Let's say this is the north side of the battery, and this is the north side of the battery. So I now have north and south looking at each other. These lines of flux are going to go from north to south. It's wrong color. How did that happen? Give me my blue. These lines of flux travel from north to south, and when I take this conductor and I move it through that magnetic field, if it's a closed loop, I will get current flow on that closed loop. The electrons will move. The magnetic field actually causes them to move. That's one of the ways that we can generate electricity, is by using magnetism. There are 6 ways to generate electricity. We'll talk about that some other time. But here's the left-hand rule for generators. The thumb is the thrust. That's the direction that the wire is going in. The forefinger is the flux. That's the magnetic flux. And the middle finger is the motive force. That's the current flow. So this is the direction of motion of the conductor. This is the magnetic flux, the forefinger, and this is the current flow. All right, so if we look down here, we'll see that we have the X, Y, and Z axis. And this one up here is thrust. This is the direction the conductor is going through the lines of magnetic flux. Z represents the magnetic flux. And X represents the current flow or electromotive force. I just called it motive force. I'm taking poetic license. Electromotive force. So I called it middle finger motive force, forefinger flux, and thumb is thrust. Okay. So let's look at what that actually does in between these two magnets. I have a north pole and a south pole, these two permanent magnets, and I have a conductor. This is looking at the cross section of the conductor, but the conductor is actually a loop of, oh boy, I'm having problems with my 3D BB today for some reason. Hold on, let me get a little bit larger eraser here. Let me see, my pad isn't positioned correctly. There we go. All right. So here's my loop of wire. And I'm going to just concentrate on this one loop of wire right here. Here it is. This is the wire. And I'm going to rotate it in this magnetic field. I'm going to take this conductor, and there's another one down here. There's two of them because here's one and here's one. I'm going to rotate this through this magnetic field. And at first, I am running parallel with the lines of magnetic flux. So this is 0 degrees, and this is 90 degrees, and this is 180 degrees, and this is 270 degrees, and back over here is 360. That's an entire revolution. So we're going to call this 0 degrees, and this is 90 degrees, and this is 180 degrees, this is 270 degrees, and then 360 is back over here at 0. So when this conductor is at 0 degrees, it's running parallel with the lines of flux. It is not cutting any lines of flux. So the voltage that we're generating in that wire is 0. But as we start to cut lines of flux, as we start to rotate and go through these lines of flux, here at 15 degrees, we're generating about 0.25 times peak. And at 30 degrees, we're generating about 0.5 times peak. And here at 45 degrees, we're generating 0.7071 times peak. And when we get to 90 degrees, we're running perpendicular to the lines of flux. We are generating the maximum amount of voltage we can generate with this generator. That's 1. And then we come back to the other side. There's 135 degrees, and that's back to 0.707. And then we get to 150 degrees, and that's back to 0.5. And then 165 degrees, we're back to 0.25. And when we get to 180 degrees, guess what? We're once again running parallel with the lines of flux. We're not cutting any lines of flux. So we're back to 0 again. So we said that at 45 degrees, we're at approximately 0.7071, which is the sine of 45 degrees, and the sine of 30 is 0.5, and the sine of 15 degrees is approximately 0.25, and the sine of 90 is 1. So if we connect all these together, we're going to start to recognize this as what's called the sine wave. And then we said when we got to 120 degrees, I believe we're at 0.866. And when we get to 135 degrees, we're back to 0.7071. And when we get to 150 degrees, we're at 0.5 again. And when we get to 165 degrees, we're back to 0.25. And then when we get to 180 degrees, we're back to 0. Now, here's the thing, and I gotta come back into the picture now. So I'm gonna reappear, and I'm gonna make myself a little bit bigger here because I want you to see what I'm doing with my hand. So let me see. Is this my left hand? I have to reverse it. Boy, I can't even get that turned around. Anyway, I'm actually having to use my right hand because I'm mirroring my image. But there's my right hand, or I'm going to call it my left hand. There's my thumb, that's the thrust. There's my forefinger, that's flux. And my middle finger, motive force. So I'm going to point my, let me try to get, oh, that's better. Get over here. I'm going to point my forefinger in the direction of the magnetic flux, and the thumb is in the direction of the flow through the magnetic field. And look, now the current is coming out of the board. A minute ago, as we were going down the right-hand side, the current was flowing into the board, and now, oops, let me get further away. And now we're going back up through that same magnetic lines of flux. So now the current is coming out of the board. So if we call this side positive, we're going to call this side negative. And that's thanks to good old Benjamin Franklin. He gave us those terms. He coined the terms positive and negative. So here, when we get to 195 degrees, we're at negative 0.25. And when we get to 210 degrees, we're at negative 0.5. And when we get to negative, what is it here, 225 degrees, we're at 0.7071. But when we get to 270, we're again running perpendicular to the lines of flux, and we're generating the maximum amount of voltage in the opposite polarity. We're generating it in the opposite polarity. I don't know how to tell you this, but there's no such thing as negative voltage. There's no such thing as negative electricity. There's electricity that's flowing in the opposite direction. And basically, that's what we're talking about. We're talking about the electrons are now traveling in the opposite direction than the direction they were just moving in a minute ago. So we call it positive and negative. This is the positive amplitude, and this is the negative amplitude. But basically, it's just electrons moving through a wire. They're either moving forward into the board, or they're moving out of the board. So positive, negative. In that same conductor, the electricity, the electrons actually stop and they move in the opposite direction as this conductor continues to rotate around inside this magnetic flux. So we go from 0 to peak positive, back to 0, and then we go to peak negative, and we go back to 0. And you can find those values by taking theta, whatever degree of rotation you use, find the sine of theta, and that's the value on this sine wave. That's why we call this a sine wave. It really is a graph of all the values of sine between 0 and 360 degrees. Okay, so let's go back to the book. Let's see what they have to say. All right. So here's a highlight. It says an electric current in a conductor creates a magnetic field that surrounds that conductor. Figure 1 shows how these principles are applied to generate an AC waveform in a simple one-loop rotary generator. So here's their version of it. Here are the slip rings and the brushes. And here's your coil of wire, and it's rotating. And I don't know which direction of rotation. They're rotating the same way I went. And the only difference is they put their north on the top and their south on the bottom. That's fine with me. That way their 0 is here. And then they got 90 degrees, 180, 270, and 360. Or just the opposite. Yeah, 0. Yeah, 180. Okay. So it says 3 factors affect the amount of voltage a conductor develops through a magnetic field. These factors include the strength of the magnetic field, the length of the conductor, and the rate at which the conductor cuts directly across the perpendicular to the magnetic field. So I'll make that a highlight. In figure 2, the magnetic field is shown as parallel lines called lines of flux. These lines always go from north to south in a generator. The motion of the conductor is shown by the large arrow. So they're saying that when this conductor is moving parallel to the lines of flux, you're getting no generated voltage. And then when we're moving 45 degrees, we're getting 0.7071. And when we're going perpendicular, we're at 90 degrees, and we're getting the maximum amount of lines of flux cut. Why do power companies generate and distribute AC power instead of DC power? That's thanks to Nikola Tesla. He was for AC, and Edison was for DC. AC won out because DC was very hard to transmit. There's no such thing as a direct current transformer. This means DC power would have to be transmitted at low voltages and high currents over very large sized wires, making the process very costly. When DC is required for special applications, the AC voltage may be converted to DC voltage by using rectifiers or by using AC motor DC generator sets. Basically, they're showing you the same thing I just did, that when we're running parallel to the lines of flux, we're generating 0 volts. And here at 90 degrees, when we're running perpendicular to the lines of flux, we've got maximum. And then when we're again running back to being parallel with the lines of flux, we're at 0. And then when we come up the other side, now we're negative. Just means it's a different polarity. It's the opposite polarity than that was assumed. It's opposite to the assumed polarity. Okay. And then we get back to 0 again. So this there's a formula that you can use. This is the formula used. It's the voltage equals voltage max times the sine of theta at any given moment, where E is the voltage induced, E max is the maximum induced voltage, and angle theta is the angle at which the voltage is induced. So we'll see that a little bit more later on when we talk about effective or root mean square. 1.1.0 sine wave terminology. Several AC terms are specific to sine waves. It's important to understand the terminology when working with AC. The following sections discuss some of these terms, including frequency, period, wavelength, peak value, average value, and effective value. Frequency is how many cycles per second. Here in the United States and Canada, we use 60 hertz or 60 cycles per second. That means that we get 60 positive peaks and 60 negative peaks in 1 second. It's the number of cycles an alternating electric current, sound wave, or vibrating object undergoes per second. Here's a highlight. It says the frequency of a waveform is the number of times per second an identical pattern repeats itself. The unit of frequency is hertz. I'm going to highlight that. Unit of frequency is hertz. 1 hertz equals 1 cycle per second. You can easily find the wavelength. How long is the wavelength? Just by reciprocating the frequency. So we said here we have 60 cycles per second. Here's 1 over x. If we reciprocate that 60, it tells us it takes approximately 16.7 thousandths of a second, milliseconds, to complete 1 cycle, 1 waveform. And you can do that anytime. If they tell you that a waveform is 0.01, let's say it's 10 milliseconds long for the entire waveform, you can just reciprocate 0.01. They say, how many cycles, how many hertz? Well, it's 100 hertz. It has 100 cycles per second. Okay. So just reciprocate the frequency. Over in Europe, they use 50 hertz. So we can reciprocate that, and we can find that their wave form, 1 cycle takes 20 thousandths of a second or 20 milliseconds to complete 1 cycle. Okay. Ours is a little bit quicker because we use 60 cycles per second instead of 50 cycles per second. So theirs is 20, ours is 16 milliseconds, 16.7 milliseconds. All right. So there again, if they give you how many cycles and how long it takes, you can divide cycles per second and get what the hertz is. So 5 cycles divided by 0.5 seconds gives you 10 cycles per second, or 10 hertz. Period. The period of a waveform is the time required to complete one cycle. The period is the inverse of the frequency and is calculated using the following formula: 1 over the frequency. So if you reciprocate the frequency, you get the time period. If you reciprocate the time period, you get the frequency. Wavelength, lambda, refers to the distance traveled by a waveform during one period. Because electromagnetic radiation travels at the speed of light, the wavelength of electrical waveforms equals the product of the period and the speed of light. Don't let that confuse you. I think our waveforms, I want to say it's just, I think it's a meter, 1 meter long, something like that. 1.1.4 peak value. Okay, now we're getting into vocabulary. We have to have a new vocabulary to talk about new things, so this is part of our vocabulary. Oh, I've disappeared on you. There I am. So the peak value is the maximum value of either voltage or current. For example, specifying that a sine wave has a peak voltage of 170 volts applies to either the positive or the negative peak. The maximum voltage level reached in an alternating current waveform in both the positive and negative direction. It's the farthest point from zero voltage on an AC waveform. In this example, the peak-to-peak value is 340 volts. You just double the peak voltage. So here they're saying from 0 to the highest peak in the positive amplitude is 170 volts. And they're saying that now I'm going to say it, and I want you to understand, this is not a valley, this is a peak. This is the negative peak. So the way I liken it is, if you're standing in the United States and this is a mountain, that's the peak of the mountain. And then when I have my whiteboard, I draw somebody upside down. I say somebody over in Europe or in China, when they're looking at a mountain, this is the peak of the mountain. So this is the peak of the negative amplitude. So we have 170 volts positive, we have 170 volts negative, and the peak-to-peak value is the highest positive value to the highest negative value. It's 340 volts in this case. Then we have two things called root mean square and average. Root mean square is effective, and it's the one that we use most often. It's the one that electricians are concerned with, and we'll talk about that in a minute. Average value is just if you took the values of this sine wave and you added them all together and divided by the number of samples, you would get approximately 0.637. And I can't do it. I don't know how to do calculus, but using calculus, you don't have to just take 20 samples or 100 samples. You can actually take every value of this sine wave and add them all together and divide by the number of samples, which I guess would be infinity. Somehow they can do it, and they come up with 0.637. So smarter people than I have done this before me, so I don't have to repeat it. I can just take their word for it. Average value is 0.637 times peak. So if we have this 170, if we're assuming that our peak is 170 volts, we can multiply times 0.637, and we'll get approximately 108 volts average. That's the average value of this peak. Now, we're more concerned with effective, and the reason for that is in alternating voltage and current, we get the same amount of work out of this AC waveform as a like value of DC at 0.707 times the peak. So if we have 170 volts peak times 0.7071, which just happens to be the sine of 45 degrees, it equals 120 volts. It equals 120 volts. How do you like that? All this time we've been telling you the receptacles in your house are 120 volts, and you've accepted that. They're actually 170 volts peak, but you don't get that much work out of them because they're only 170 volts for a very short period of time, a blink of an eye. Most of the time, they're less than 170 volts. And the way I explain it is if we cut the top of the mountain off and we fill in all the valleys, we end up with this 0.7071. There's more to it than that, but suffice it to say that the effect that it has on a resistance is the same as a 0.7071 times peak of a DC value. If I had 120 volts DC and I put it through a 10 ohm resistor, well, now I've hurt myself because now I need my calculator. So it would be 120 squared divided by 10 ohms. I would get 1,440 watts of power out of that circuit. And I will get that same 1,440 watts if I had 170 volts peak of AC. I would take the effective value, 120, and I would square it and divide by 10 ohms. And it would give me the same 1,440 watts, or in this case, we might call them volt amps, of power in that AC circuit. Okay, so let's go over our vocabulary. 1/2 of the sine wave is an amplitude, a positive amplitude or a negative amplitude. The entire sine wave is called one cycle. The highest value in either the positive or the negative amplitude is the peak, the positive peak and the negative peak. And the value between the positive peak and the negative peak is called the peak to peak. The highest positive value to the highest negative value, and yes, I'm going to call it the highest, even though to our eyes it looks like a valley. It's the highest negative value. Remember, there's no such thing as negative electricity. It's just electrons flowing in the opposite direction, okay? So that's our peak-to-peak value. And then the effective value, the value of work that we can get done with that AC waveform is the effective value, or the root mean square, 0.7071 times the peak value. Average is something else. Average is 0.637, but we only get it when we convert our AC waveform into DC. So I don't want to confuse the issue, but oh, that's horrible. Let me try that again. Why am I not getting straight lines today? I just can't seem to get my board set up. So here's my AC waveform. Oh, that's horrible. Gee whiz. I guess if I slow down and I think about what I'm doing, maybe I can do a little bit better. Now, out of this, I'm going to get 0.7071 times peak. That's how much work I can get done, and that's called the effective value. It's also known as root mean square. But if I take a rectifier, and we don't really know what that is yet, so don't worry about it. We'll find out what a rectifier is here in a minute. If I take a rectifier and I flip all of the negative amplitudes over and make them positive amplitudes, now I'm not going to get 0.7071 times peak. I'm only going to get, and I'm going to use a different color, 0.637 times peak. I'm going to get the average of the values of those amplitudes. So when we convert to DC, when we turn all of the negatives over and make them all go in the same direction, it's pulsating DC, we're only going to get the average value, 0.637. That confused me for a while when I was an apprentice, why we had effective and average, and they were both a way of figuring out the, the mean of these values. Well, one of them is AC, one of them is DC. That's the difference. When you rectify it into DC, you're going to get 0.637, the average. But if it's still a sine wave, and they ask you what's the effective value, it's 0.7071 times peak. I hope that cleared it up. Hold on, let me see here if I can get back to my book. All right, I didn't get back to my book. What happened? All right. So there's your average value, 0.637 times peak value. That gives you average. And here's effective value. Meters used in AC circuits indicate an effective value. So when you put your meter in the wall, it doesn't tell you it's 170 degrees. It tells you it's 120 degrees. It takes into consideration the root mean square, and that's the way they find the value of the effective value. It's long and drawn out. Suffice it to say, they use calculus and they come up with this root mean square. It's the root of the mean of the square. They take all of the values of that sine wave, just like an average. They take all the values and they add them together and divide, and they get an average. This one, they take all the values of the sine wave and they square them. Then they take the average or the mean, and then they take the square root of that. So it's the root of the mean of the square. We square it, then we mean, average, and then we root it. But we don't say root of the mean of the square, we just say root mean square. Okay. So meters used in AC circuits indicate a value called the effective value. The effective value of an AC current or voltage is the measure of energy transfer that is equivalent to a direct current or voltage. That's why it's effective. In a DC circuit, the current maintains a steady amplitude. Therefore, the heat produced is steady and is equal to I squared R. In an AC circuit, the current's continuously changing, periodically high, periodically low, periodically zero. To produce the same amount of heat from an AC as from an equivalent amount of DC, the instantaneous value of the AC must at times exceed the DC value. So here it is. This is the root mean square. It's the most common method of measuring a sine wave of voltage or current is by stating its value at 45 degrees, which is 70.7% of peak. This is its root mean square, the multiplication of the square root of the mean average value by the squared function of the instantaneous values throughout the period. The root mean square value of an AC voltage or current is the effective value of the voltage or current. So the more you know. I wish I had that thing behind me. The more you know. So here's a highlight. Value of root mean square equals 0.707 times the peak value. For example, with a peak of 170 volts, the root mean square value is 0.707. It's actually 0.77071 if you want to get exact, times 170, which equals approximately 120 volts. Now, here's a freebie. I'm just going to give this one to you. They don't say this in the book, but here's 170 times 0.7071, and that's 120 volts. And here's 170 volts times 0.637. It's 108. Watch this. 108 divided by 120 equals 90%. So it's an easy rule of thumb that your average value is about 90% of your effective value. If you have the average value, oops, I didn't mean to do that. If you have the average value, if they tell you it's 108 and they say, what's the effective value? Just divide by 0.9 and it tells you 120 volts. If they give you the effective 120 and they say, what's the average? Just multiply times 0.9 or 90%, 108. So that's a shortcut. Root mean square amplitude. All right. Root mean square value, also called the effective value, is the value assigned to an AC voltage or current that results in the same power distribution or dissipation at a given resistance as DC voltage or current of the same numeric value. As shown, a peak voltage of 120 volts AC will not produce the same light as 120 volts DC from a 60-watt lamp. To produce the same light, 120 volts RMS must be applied to the lamp. This requires the applied sinusoidal AC waveform to have a peak voltage of approximately 170 volts. And that will give you about the same output as that DC 120 volts. You can't use the AC 120 volts. Here they're not getting 500 lumens, they're only getting 350 lumens. So when they use the 170 volts peak AC, then they have 120 volts effective value, or RMS, and they're getting the 500 lumens out of the light bulb, the same as the 120 volts DC. All right, very good. 1.2.0 AC phase relationship. In AC systems, phase is involved in two ways: the location of a point on a voltage or current wave in relation to the start of the wave, or in relation to a corresponding point on the same wave. In the case of the two waves of the same frequency, it is the time at which an event takes place on one wave compared to when a similar event takes place on the other. So they're going to talk about phase angles. Let me start a new video, and I'm going to talk about phase angles. I'll see you on the next video.